lastly, I moved up the due date to tomorrow at 11 p.m. so you guys can look at that before your quiz on Thursday, which will be over 354, 3536. Question?
I just have a general question, and
Okay.
there's a couple of wily ones about it, but it's in 3.6,
L'Hopital
and it's
rule.
where you end up with e to the like 10 over pi.
Yeah.
And I don't understand where the e comes. How you get the e out
Okay.
of that?
The E comes from this because I can evaluate this limit, but I could evaluate the limit of ln of y. So I go through and take ln, I call this function y, and then I actually did this one today in class, so in the other section. So let's just take a minute, and I think I did it in your section too. So I can't begin to evaluate this limit. It's in type 1 to the infinity power. When we learned about indeterminate forms, we only know 0 over 0, infinity over infinity to apply L'Hopital's rule directly. But we talked about other indeterminate forms that we can manipulate to get into the form 0 over 0 and infinity over infinity. One of these was 0 times infinity. So if I have 0 times infinity, I can always move one of those down in the denominator, take it to the negative power, don't change the expression, but you get it in the form 0 over 0 or infinity over infinity. So the next type is 1 to the infinity power. So this is just more layers. So the first thing I want to do here is I want to write the function y as this function. I would really like to find limit of y, but I can't do that. I can evaluate the limit of ln of y, and then once I have the limit of ln of y, if I take e to this power and e to this power, then e to the ln of y is simply y, right? And then so if I take e to this side, I have to take e to this side, so I get e to the power. It's the property that ln and e are inverses of each other. So if I have the limit as x goes to 1 of ln of y equals 8 over 10, if I take e to this side and e to this side, well, the property of the limit, I can move this in. So I'm taking the limit as x goes to 1 of e to the ln of y equals e to the 8 pi. E to the ln of y can simply be written as y. So now I found the limit of y, which was my original approach, my original thing I wanted to do. But I had to kind of go about it backwards and take the limit of ln of y, because then I could manipulate it to have 0 times infinity. And then I can manipulate that to have that 0 over 0 to apply what's called rule and get an answer.
You know, that very last step that confused me.
Does that make sense?
That
Now, that the limit of ln of y is an answer. So the limit of y is going to be e to that answer. And so once a lot of times students will forget that. They're so glad they get somewhere. And it is a lot of work, and this is just kind of takes 2 seconds to get, and you have to remember that. So a lot of times I always write ln of y at the beginning to reaffirm that this answer is the limit of ln of y. But I don't want the limit of ln of y, I want the limit of y. So I need to take e to that power, because e will cancel out the ln. All right, so if I take e to the ln of y, that just gives me y. And yeah, so on that one, anytime you're taking logarithmic differentiation, you're really finding the limit of ln of y. So to find the original limit of y, you have to take e to that power.
Do you just know that tangent of pi over 2 is x goes to 1, or yeah.
So this is going to
based
pi
on
over
the graph.
2, yeah, from the graph of tangent. And it's actually positive infinity or minus infinity, but it doesn't actually change with ln of y, because it would be only off by a constant. So tangent of pi over, well, it's actually tangent of x. If I was to graph this, it's undefined at minus pi over 2 and pi over 2, and it looks like this, right? And it's periodic, has a period of pi. So if I approach it on this side, I go to infinity. If I approach it on this side, I go to minus infinity. But that's only off by a constant with ln of y. Because if I have ln of y, if y is negative, then I could write that, well, if it's like the minus power, I can write that as minus ln of y. So it doesn't matter if I take 1 to the infinity or 1 to the minus infinity. It's still going to approach the same thing. It's going to approach e to the minus, or e to the pi over 10 or pi over 8, depending on your numbers. So yeah, from the graph, I can say this is going to infinity. It would be quite a bit more clear if it was a one-sided limit, because you can say, oh, this is going to positive infinity or it's going to minus infinity. With 1, when I have 1 to the infinity, or if I have 1 to the minus infinity, it's the same thing, right? 1 to the infinity is the same as 1 over 1 to the infinity. So in this case, you can take the limit on the right or the left, so it's not one-sided. Make sense kind of there? Because, yeah, on the left side of tangent as it approaches pi over 2 is positive infinity, but on the right side it's minus infinity. So you wouldn't think necessarily the limit exists, but it turns out this is the same thing. The same indeterminate form. But those are good questions. Any other questions on 3.6? Or 4.1? You guys have? I know you probably most likely didn't look at it since the due date's April 1st, and you have the quiz to focus on this Thursday, so you'll have plenty of time to ask questions on that later. After spring break, this is due the Monday we come back from spring break. So you'll have that Monday to ask questions in class and have all spring break to look at it. Nothing better to do on spring break, right? 3.4.
I got the answer, but I did it like a million times too.
So did I talk about the relationship between H and R in this class, or was that the other class? On the cone problem. Most of you are looking like I didn't talk about it. Okay, so let's look at today's 3:19. So this is 3.4, number 25. So this problem is relatively involved because the volume function, so first off we want to know how fast the depth of water is increasing. So we're looking for dH dt. And we're given the water flows in the tank at a rate of dV dt. So we really need a function for volume only in terms of the height, right? So let me just draw this picture real quick. So I'm given the radius of the tank to be 9 feet at the top and the height of the tank to be 24 feet. dV dt was given as 20 feet cubed per minute, and the height is given to be 16 feet. At the instant in time when the height is 16 feet, I want to find dH dt. What is the change in height at that instant in time? When I pour water into here at a constant rate of 20 feet per second, the volume is changing. But the height at first is changing a lot, and then once it gets up here, it's not changing as fast. So I want to freeze time when the height of the water is 16 feet, and I want to find how fast the water is changing height at that instant in time. So what is the formula for volume of a cone? So I have volume, I have radius, and I have height to deal with. But I don't have a dr dt, so I can't differentiate this in terms of t because I would get a dr dt and I don't have that. So I want volume as a function of only h. So I need to get h, I need to get r as a function of h. So the way to do that is saying this is the height, let's call that h. This is the radius, let's call that r, right? So when the height of the water is h, the radius of the water is r. When the height is 24, the radius has to be 9. You guys see that? So I just called my height h and my radius r. So what would be a way to relate 24 to h and 9 to r? Similar triangles. Multiple different ways to write it. I can say 24 divided by h is going to be the same ratio as 9 divided by r. But there's about 4 other ways you could write that too. So now I would have 24r equals 9h. So I'd have r equals 9h divided by 24. So this is a function of h. So now I have volume is 1/3 pi. R is 9h over 24 squared times h.
Could you simplify that?
Well, I could simplify it. I would have volume is 1/3 pi 81 over whatever 24 squared is times h cubed. So all this is just a constant. Agreeing it's an annoying constant, but it's a constant. So differentiating it is not going to be a problem, right? This is really where the work is put into it, getting a function of only in terms of h. Most time you don't have to deal with that. Anytime you're like a circle or a sphere, it only depends on the radius. So you only have one function. But when you have anything that is changing the radius and the height at the same time, you're going to have to manipulate one in terms of the other. And you could have easily solved for h in terms of r, plug that in for h, and have a function of only r if you wanted dr dt. So now differentiating this with respect to t, I have dv dt, which is given. I have 1/3 pi 81 over 24 squared times 3h squared times dh dt. Right? So the 3's would cancel. I want dh dt, so dh dt would be dv dt times 24 squared divided by 81 pi h squared. Right? So I divide by 81 pi h squared, and I multiply by 24 squared. And I evaluate this when h is 16 feet. So I get dh dt, and then dv dt is also given as 20 feet cubed per minute. Make sense on this one? So if I plug all that in, you get your answer.
One of the things that took me a while is that you have a huge square root number. And so I
To
had
simplify
yeah,
that?
to simplify the square root
Yeah.
without a calculator that tells you.
Most calculators can do that,
Mine didn't.
but yeah, before. There you go. And on the exam, on the final exam, on the quiz, to be honest, you're not going to have to simplify anything. Plug it all in your calculator and get a decimal. That's perfectly fine. Most of the numbers will come out nicely. You won't have anything crazy, but Wiley likes to throw some curveballs at you. But you it shouldn't be too time-consuming to simplify that. Any questions on this?
How did you get h to the third?
Here, I have h squared times h,
Oh,
which would be h cubed, which makes sense because it's a volume, so something has to be cubed. Here I have r squared times h, so my units would be cubed. Here my units are just going to be directly cubed. So this formula is for volume of a cone that has a height of 24 and a radius of 9. So you only have to know the height to find the volume, which makes sense because the height and radius are related. Right? And there's a ratio. If I know the height, you can find the radius if you know the volume by plugging it into the volume formula. And that's essentially what we did.
I looked in the solutions manual to figure it out. I feel like they just did it way differently, or not different. It was just, like,
Possibly.
a lot more steps and just like confused.
So, someone have a calculator, they want to plug this in? 20 times 24 squared divided by 81 times pi times 16 squared.
Yeah, that's not going to give me a nice number. And oh, sorry.
You're good.
Oh, wait. Could not work. So 16 squared. What do we have? We have 20 times 24 squared over 81. Leave the pi out.
1 over 36 pi.
So leave the pi out of your calculator. What is 20 times 24 squared divided by 81 divided by 16 squared? Put that in fraction form. Can you put it in fraction form?
It would have been easier to do 3 over 8 for the 9 over 24. Probably just like watching.
9 over 24 squared, yeah. I could do that.
So you
3 over 8.
From the original part.
Yeah.
If we reduce that 9 over 24 to.
So if I divide both by 3. Mm-hmm. Let me see your calculator.
Then you have
It's
20
5
times
over 9
64.
pi.
5 over 9 pi. So we have 20 times 24
5 over 9.
squared. So
I had one of the weird numbers
Oh, wait.
set, so I had like 243 over like 655. I just didn't use the numbers.
So 11520.
5 over 9 pi.
You got 5 over 9 pi?
Yeah.
So if I take 11520 divided by 2. And I got, if I can go to fraction to decimal. So I got that as our answer. I got 9 over 16. All right, so let's see what we get here. I will take your guys's, since both of you guys got it. So you got 5 over 9 pi. There you go. So let's look at the solution here. So looks like they're doing the same thing. They simplify their numbers earlier, right? So they're trying to find what's the rate of change of the height when the height is 16. So they get the formula for volume, and then they need to look at similar triangles to find r as a function of h. And they plug that in, they get h. Okay, so they get v equals this. And then differentiating it, they simplify their constants. And we just left all of ours. They solve for dh dt, so they have this, which is probably what we would have if we multiplied out our constants and dealt with that. And they get the same thing with that there. Looking at a different solution manual or this
Well,
one?
no, I meant like the actual solution manual, like for our book.
The student solution manual?
Yeah.
Okay.
I feel well. Sometimes they like skip steps, and I just
Yeah.
like all of a sudden they like come up with some other number, and I have no idea where it came from.
It'll
So I
Yeah.
step by step on that.
So yeah, solution manuals generally are written by grad students that have 15 other things going on. So sometimes they're right, sometimes there's errors. Humans put them together, so not to say that everything in there is exact. We are on the 10th edition though, so hopefully some of the bugs have been worked out. So does it make sense now? You feel like you could do a problem like that on an exam
Yeah.
or on a quiz?
Well, we could get a formula for like.
If you, yeah, if it's anything crazy, like on final exams, I've seen them give formulas for area of a circle just so it's there.
So most likely, if you need a crazy formula, you'll be giving it to it. Like volume of a sphere, cone, yeah, something like that. That's usually given. Usually the volume or the area of a circle is not given, but I've seen it given on finals. So, okay, so today we're going to talk about 4.2, which is a lot of the same things. We're going to specifically talk about the same things we've been doing. We're going to give a name to the first derivative test and the second derivative test. And our whole goal in this section is to be graphing polynomials. You guys graph polynomials in college algebra. You found like the x-intercepts, the y-intercepts, the end behavior, and then you connected the dots. We're going to do that one more step to say we know now we're going to be able to find maximum and minimum points. So you find the x-intercepts, you find the y-intercepts, you find the maximum and minimum points. You know concavity, is it concave up or is it concave down? So something can be positive slope in concave up, or it can be a positive slope in concave down. So now, instead of just connecting the points, you're going to know you're going to connect them with a concavity up or concavity down type slope. So it's just kind of putting all these different terminology together. We're going to define critical point, and we're going to define stationary point and what that means to the graph of the function. So this is 4.2. Analyze or analysis of functions, part 2. My pen's dying. Graphing polynomials. So the nice thing about polynomials are continuous everywhere and differentiable everywhere. So we're not going to have to worry about any jumps in our graph. When we talk about graphing rationals, we have to look at points of discontinuity, vertical asymptotes, things like that. So we're going to be doing the same type of thing with just more complicated functions as we go. So relative maximum and minimum points. These are known as extremum points. And they're all relative on some interval. Eventually we'll talk about global maximum and global minimum to say on the interval, on any interval, what is the highest point and what is the lowest point. Which you guys did applications of this in college algebra for like maximize your profit. So you're going to be within some interval, which would make sense, and you want to maximize your profit. So if you had a revenue type function, you graph that, the x value, there's a perfect x value that's going to maximize your profit. Now in real life, the problems aren't that simple. You have a lot more factors. So if you change one factor or another factor, how that affects the graph is really what you'll get into in Calc 3 if you get that part. But relative maximum and minimums. So just to kind of throw an example on a graph. So if I have a function that looks like this, I have maximum points, right? All these little hills here are maximum. I also have minimum points here. And we only ever talk about a relative area. So in this interval, this is a maximum point. But it's not necessarily a global maximum. This would be the global maximum. Granted, this function didn't go off to infinity. So we're going to focus on relative maximum and minimum points. So only on an interval is it the maximum point on it. Do you notice something about the derivatives? If I go from a positive slope to a negative slope, that gives me a maximum. If I go from a negative slope to a positive slope, that gives me a minimum. And we're going to verify that with the first derivative test. So the first thing we're going to define is critical points. A critical point is defined as the point or points on the graph f of x, or of the function, that has a horizontal tangent line or is not differentiable. Now, polynomials, we're not going to have to worry about differentiability, right? They're continuous everywhere, they're differentiable everywhere. But if I get to a little bit more complicated functions, if I take the derivative and the derivative doesn't exist at that point, that's a critical point. Or if the derivative equals 0, that's a critical point. More so, a stationary point is a type of critical point of the function where f prime of x equals 0. So x would be a stationary point if the derivative equals 0. It's a critical point if the derivative equals 0 or is undefined.
Wait, can you say that again?
So this is a common thing students struggle with is the definition. So a critical point would be where the derivative equals 0 or it's undefined. A lot of times we'll talk about undefined when we have like a corner. A stationary point is when the derivative equals 0. The first derivative equals 0. So if I was to kind of graph some examples here, so I could have, so this is the function f of x. Then I have critical points here. Right? Those are my critical points. I have a horizontal tangent here, a horizontal tangent here, and a horizontal tangent here. This is an undefined tangent. My tangent's undefined. My derivative doesn't exist at that point. If you recall back the function y equals absolute value of x, I have a function that looks like this, right? The derivative is minus 1 or 1. Do you guys remember doing that by the definition of the derivative? So this is a critical point, but not a stationary point. So this point here,
So a point is what you're saying?
yeah, a corner, it's going to be a critical point, but not a stationary point. And these are critical points that are stationary points, because more so the first derivative equals 0. So this is a critical point. But not a stationary point. So that also talks for this point and this point. But the rest of them are critical points and stationary points. A stationary point is a critical point that when the first derivative equals 0. It's kind of a question.
Could you be consistent with the terminology of the definition of critical point? If a stationary point and say where tangent line, where there's a horizontal tangent line, would be the same thing?
It would not be saying the same thing because you would forget about the differentiability. Polynomials, your only critical points will be stationary points. But in a rational function, a critical point is going to be also where the derivative doesn't exist. And we'll do an example of that. So if I take a derivative of a function, let's say x to the 2/3. What is the derivative of x to the 2/3? Right? So this can be written as 2 over 3 the cube root of x. Right? Well, when does this equal 0? Well, it never equals 0. Because the x cannot equal 0. So this is a critical point, but the function is defined as 0. Right? X of 0, if I plug x equals 0, the function, I get 0. 0 to the 2/3 is 0. But if I differentiate this and I plug in 0, I get not defined. So that's a critical point, but not a stationary point. Because if I plug in 0 to the derivative, I get something that's not defined. Make sense? So critical points, two cases. They're either stationary points or just critical points. Critical points would be when the function's, well, I kind of said that. A stationary point is a critical point. So if the derivative equals 0, you have a critical point, and more so you have a stationary point. If the derivative doesn't exist at that point, you just have a critical point.
And when the derivative equals 0, you don't necessarily have a horizontal tangent line?
No, you do. When the derivative equals 0, you have a horizontal tangent line. Right? Because that means the slope is 0.
So that second line could be right. could replace
Yeah.
horizontal tangent line.
with the derivative of the function equals 0. Okay,
That just
does that?
confused me where they
Yeah,
changed.
horizontal tangent line, if I wanted to come in here, this has a horizontal tangent line, right? This has a horizontal tangent line, this has a horizontal tangent line. But all the other tangent lines are not defined. I don't have a tangent here, it doesn't exist. So at this point and this point, then f prime of x does not exist. It's undefined. So it's not a stationary point. It's just a critical point. A critical point where the derivative equals 0 or has a horizontal tangent would be a stationary point. Question?
I'm just confused that you replaced horizontal tangent line with f prime of x equals 0, and stationary point is.
A critical point, a stationary point is a critical point. It's a
But
special.
this. Oh, okay.
Yeah, here, or.
I was backwards. Stationary point is the ones where they have the horizontal tangent.
Correct. So you can also think of stationary as the rate of change is 0, right? So it's not changing, it's stationary. But when the rate of change doesn't exist, the function can still exist at that point, but it's just a critical point. And it can still be a maximum or a minimum point, right? I have a maximum here and a minimum here. The function exists, but the derivative doesn't. So it's not differentiable at that point. And we'll see some examples of this and see how that works out. Okay, so let's look at an example. So
For the one you put on the board, that does not exist as well because the denominator would be 0, right?
yeah, the derivative, if we wanted to find critical points, there's one critical point,
Yeah.
and that's at x equals 0.
Okay.
And it's not a stationary point, it's just a critical point.
Got it.
A stationary point would be also the case where the numerator could equal 0 or something like that. Okay. So this example, we want to find all critical points. Okay, so we have f of x equals x cubed minus 3x plus 1. So the critical points are going to be where the first derivative equals 0 or is undefined. Nice thing about polynomials, the derivative is always defined, right? The derivative of a polynomial is a polynomial which is continuous everywhere. So if I differentiate this, I get 3x squared minus 3. When does that equal 0? Well, when 3x squared minus 1 equals 0, so when 3x minus 1x plus 1 equals 0, right? So my critical points are when x equals 1 and when x equals minus 1. A lot of times when they say critical points, they want an x value and a y value. Where does this point on the graph? Well, so if I plug x equals 1 to my function, I get out 1 minus 3 plus 1, so I get out minus 1. So 1 comma minus 1 is a critical point. The x value is given. If I plug in minus 1, I get 3, 4, minus 1, which would be 3. Does that make sense? So if I was to graph this, if I find the x-intercepts, the y-intercepts, all this different thing, if I look at the graph, I don't have too much room. So this is a cubic. The end behavior goes from minus infinity to infinity. But at minus 1 and 1, I have my turnaround points. So at minus 1, I plug in 1, I get 3. And at 1, I plug in 1, I get minus 1. So if I connect these dots, and I go off to infinity, you can see that from the derivative test, if I look at, this is eventually where we're going, if I mark minus 1, 1, if I plug in a number to the derivative that's less than minus 1, let's play I plug in negative 5. I have a negative, positive, so that'd be negative. If I plug in 0, I have a negative, positive. No, sorry. If I plug in negative 5, I have negative, negative, which is positive. If I plug in 0, I have a negative, positive, which is negative. And then if I plug in 5, I have positive, positive, which is positive. So you can see I have a positive slope and a negative slope, and then a positive slope. That tells me that this point is a maximum and this point's a minimum. But do you guys see that from the graph? You wouldn't have to graph it to get that. You could just show the first derivative test. Positive slope to a negative slope, this is a maximum. A negative slope to a positive slope, this is a minimum of the graph. But this is the overall shape of the graph. It's increasing, and then at this point it's decreasing, and at this point it's increasing. I didn't have to do the derivative test to show that, right? Once I know the end behavior, and I have these two dots to connect, I know it's going to go like this. There's no other options. It's continuous, so I can't lift up my pen. I need to connect this to this to this to this. It has to be in this shape. Turns out you can do a little bit more work here. And if I take the derivative of this, I get 3x. Set that equal to 0. My critical point is at 0. If I plug in a negative number, I get a negative number. If I plug in a positive number, I get a positive number. It tells me it's concave down from minus infinity to 0 and concave up from 0 to infinity, which makes sense from the graph, right? Question?
Whenever you did your number line there,
Yeah?
Did you plug in the numbers into the 3x squared minus 3, or did you plug it into?
I plugged it into the derivative. So this is a common thing that students get confused. When I'm looking for a point on the graph, this is my critical points, right? If I plug the point into my original function, I get the point on the graph.
Yeah.
But if I want to know if my slope's positive or not, I plug it into the derivative, right?
Yes.
So here I'm plugging it into the derivative function. So if I plug in minus 5, I can't go up here. Minus 5 squared is a number larger than 3, so when I subtract 3, I get positive. So that gives me positive. But a lot of times you plug it in the factors. And so if I take minus 5 minus 1 is negative. Minus 5 plus 1 is negative, and a negative times a negative is positive.
I guess that was my question because it's a lot easier just to plug it into the unfactored part.
Sometimes.
For some people. Just depends how you
For
think.
some, yeah. It depends on how many factors you have, and it depends on the number you pick. If I plug in 0, clearly it's minus 3, right? Plugging in 0 here, I have a negative times a positive, it's negative. You can pick in which one you want to plug it into. If this is really, really long, it might be easier to plug it in. Each term is positive or negative. Does that make sense? But yeah, you can plug it in any level of this, as long as you're evaluating the derivative. So just to kind of go through and show you, if I take the second derivative, what is the second derivative of this function? 6x, right? If I set that equal to 0, my critical point is at 0. If I plug in a negative number, I get negative. If I plug in a positive number, I get positive, right? So this is telling me I'm concave down. And here I'm saying I'm concave up. Eventually, we're going to learn the second derivative test. And the second derivative test says if I plug in my critical point to my second derivative and it's negative, then I have a maximum, which makes sense, right? If I have an area that's concave down, my critical point's a maximum. If my area is concave up, my critical point's a minimum. So instead of like memorizing all this, if you think about it, you're better off to say, okay, if I have a positive slope on this side and a negative slope on this side, I have a maximum. If I have a negative slope on this side and a positive slope on this side, I have a minimum. Because eventually, depending on what they ask you, they might only ask for the maximum points. They might only ask for the minimum points. But you have to test all of them to go about that.
So for this, at 0, the whole thing is concave up to the right and concave left. Or concave down.
0 is my inflection point, right? So this is concave down, and this is concave up. Which we knew that from the graph. clearly we can see that. This is just verifying it. They might ask you for the intervals on concavity. So here you would say minus infinity to 0 is concave down, and 0 to infinity is concave up.
So the second derivative is always finding concavity.
Correct. And you can use the second derivative to verify maximum and minimum points, right? Minus 1 falls in this interval. And if I plug in minus 1 to the second derivative, I get a negative number. So that tells me I'm concave down. So that tells me my maximum point is my critical point's a maximum point. If I plug in 1 to my second derivative, I get a positive number. So it tells me I'm concave up in that interval. So I know it's a critical point. If it's a critical point on a concave up interval, it's a minimum. So let's kind of write some of this up. So we have the first derivative test. The first derivative test and the second derivative test is a way to classify critical points as maximums or minimums. So I believe this is 4.2.3. So a function f of x has a relative extremum at those critical points where f prime of x changes signs. Which makes sense, right? So if I do the first derivative test, and I take the first derivative, and let's call x naught this point here, and I have a positive slope on the left and a negative slope on the right, that verifies that this is a maximum. Makes sense, right? Positive slope to a negative slope, it has to be a maximum point. So f of x is a maximum point. And so the point x naught comma f of x naught would be the point on the graph. Huh? Because I have a positive slope on this side of the point and a negative slope on this side of the point. So everything is getting larger, 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 then smaller, 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 smaller. So this would have to be a maximum. That's the first derivative test. If I have a first derivative test that looks like this, then x naught is a minimum point. And you always plug it back into the original function to find the point on the graph. Maybe this should be on instead of. If I have a negative slope, and then on this side I have a positive slope, this has to be a minimum, right? If I have both positive or both negative, it's neither a maximum or a minimum. That happens in the case, if you look at an example of something like this. This is still a critical point because the derivative equals 0, but it's not a maximum or a minimum. So the first derivative test would show that it's not a maximum or a minimum. The second derivative test is very similar, but it doesn't always work. The first derivative test always works. Second derivative test can be inconclusive. So the second derivative test. So the second derivative test is 4.2.4 in your book. And basically what the second derivative test says, if the derivative of the function at a point is 0, makes sense, it has to be a stationary point to be a critical point. So if you have a critical point and you plug that critical point into your second derivative and that's positive, then your function has a relative minimum at x naught. You're always better off thinking about what's going on. A lot of times students will say, oh, it's a maximum then because it's positive. Positive number's big, max, but no. And concave up means that you hold water, right? Positive means you're concave up. If you hold water, then your critical point is a minimum. Make sense? If you're concave up on that interval, your second derivative is positive. If your second derivative is positive, you're a minimum point. B of this theorem is if you have a critical point, so if the first derivative equals 0 and the second derivative is less than 0, then the function has a relative maximum at x naught. And C is if the derivative equals 0 and the second derivative equals 0, it's inconclusive.
So the first derivative test is just better.
The first derivative test is a little bit more powerful. The second derivative test actually comes in handy when we get into the application problems. And I say this is one critical point. Verify it's a maximum or a minimum. And I don't necessarily give you any information to evaluate the first derivative, but I give you enough information to evaluate the second derivative. So I could say something about the concavity, or if you can say, this is a critical point and the second derivative is positive on this interval. If it's positive, it's concave up, and you know you have a critical point, you know it's a minimum. So eventually, there's opportunities to use the second derivative. A lot of times that happens on quadratics. Now quadratics, you're only going to have one critical point, right? The vertex. So if I have a quadratic and this is a negative slope and a positive slope, clearly it's a minimum. But you can also take the second derivative of a quadratic as a constant, right? And if that's positive, it's concave up, meaning this is a minimum. So it has some applications when we get into the application section. And you guys have seen something like, I know in college algebra you probably did something where you give it a fixed perimeter and you had to maximize the area.
Yeah.
It came to a quadratic and your maximum was a vertex. So you're going to do the same thing as when you have that quadratic, you differentiate it, set it equals 0, and you get the vertex. And then verify if it's a maximum or a minimum. All right, so we're kind of running out of time today. I will do some more examples of this tomorrow. But, I mean, in all honesty, it comes down to your algebra, being able to set these functions equal to 0. Differentiating a polynomial at this point should be pretty straightforward. Eventually, we'll talk about rational expressions. When you differentiate it, you have to use a product rule, and then you have to set that equal to 0 and solve for that. So I will see you guys tomorrow.